Okay, good. Then let's get started. So today we want to talk about the assignment, first assignment in the Intelligent Humanoid Robotics course, discussing kinematics, dynamics a little bit, and control. And to remind you, the interesting part of the assignment is you have a humanoid robot with a plane mounted on its head, and then we play a little marble game. So we have a plane with the ball mounted on top and a vision system. Looking down onto the field, and then from the top it would look something like this. That's the ball. And now you want to control the ball so that the ball stays in the center of the playing field by tilting the body of your humanoid robot. So the question then is, why is that tricky, or what makes that difficult? The first part of the assignment, you have to roll the ball through some kind of maze. From a start location to a goal location. Something like that. But here, the tricky part is that the situation is much more dynamic. So you actually need to worry about the forces acting on the object. You need to worry about the velocity at which things are rolling and moving in the domain. So now, if you have never taken any control theory course, then what would be a good algorithm? What would you implement in order to try and balance the ball? As a first idea or first cut. And of course, there's lots of control problems in robotics. We also had the first one that we were dealing with at the University of Auckland. That would be this problem here. And there the challenge was we had some path and we had a car that we can control, the steering angle and the velocity, and then the goal was to try and drive the car along the straight line. Something like this. So now, for this particular problem, what control strategy would you come up with? So you just want to be able to drive the racetrack here. Initially you can ignore velocity, you just assume that you're driving at a constant speed down a straightaway. Then what steering angles do you need to pick, right? That will be the problem here. So you have the car, position of the car, the position of the wheel, and there's some steering angle alpha, and you need to control the steering angle. So when we did that with the students, then a couple of them said, well, that problem is not particularly difficult because all we need to implement is the following algorithm. Step 1, if the car is to the left, so here we have a...
Okay, so I'll start recording. Good morning, everybody. And today's class, I want to introduce assignment number 2, the project, which is going to be part of the Global Virtual Classroom initiative.
Oh, that's why, okay.
NTNU. So this project...
Don't tell me that it's, Bamboleo.
...will be done in conjunction.
Right. So, 1, you need to mathematically define your problem. Now, what value, you need to have some kind of function, right? And the output of that function should be a steering angle alpha, right? Because you need to control the steering of the car. If we look at the balancing the ball here, then what would be the output of our control? The what? Yep, that would be one way to model it. So let's call that angle theta or gamma. The theta we use for the joint. That's one way of modeling it, and probably a pretty good one. Of course, you could also say you want to model the output should be theta 1 to theta n, where this would be the state of your robot. That would be another way of modeling it. However, since you can control the kinematics, assuming that you know what tilt angle you want on your platform, you can calculate from gamma what theta should be. This will probably be easier to do it that way. So your controller determines what the tilt angle of the platform is, and then once you have the tilt angle of the platform, you come up with an algorithm to implement the kinematics, the inverse kinematics, so that the platform will be at the correct angle. So for the car, what will be the input to the function? What do you need to know in order to determine what alpha should be? Yeah.
The current angle and
The what?
the current angle
The current angle of what?
of the car, like the heading.
Right. So the heading of the car. Yeah.
And the goal heading.
And the goal heading. So the direction of the line. Yeah. Anything else? Yeah, we usually also need to know that distance between the car and the track that you want to follow. So let's call that D, and let's call that difference here theta tilde. And you'd have D and theta tilde. And for our ball rolling thing, ball rolling maze, what would be the input for our control function? What? Yeah, that would be one input, yes, but that would be difficult to design a controller based on just the pixel values, right? So if you try to develop a control for this, then what would be important, the important part of the image that you would be looking at? I would think that definitely you would need to know the position of the ball, right? So let's call that P, P, P. Anything else? Yeah.
Velocity and acceleration of the ball would be useful.
Yep. Maybe velocity, acceleration. So the velocity, if dp is your position, then the velocity of the ball, if dp is the position of the ball, velocity of the ball would be the first derivative of the position with respect to time, which we abbreviate as dp dot, and then the second one, the acceleration would be dp dot dot. And that's probably all you need. You can also include the current angle, so gamma prime or something, because that may be important too, right? If the plane is tilted like this or tilted like that, may change the decision that you make about what control command you want to set. Now, with this problem here, I had a hard time with the students because they said, well, that control function is pretty easy because we simply need to implement if d is greater than 0, which means we're to the right of the path, then, and the cars that we had only had digital control for the steering. So we couldn't go 10 degrees, 12 degrees, 15 degrees. The only thing we could do was full left, straight, and full right. It was a very cheap toy car, right? So because of that, they came up with the control law that if d is greater than 0, then we turn left. So alpha is equal to 20 degrees. Else, what do we do? Else we turn right. And that was the control that they wanted to implement. And it was very difficult to actually convince them that this will not work. And why it won't work, we'll go through an example, through a different example just now. But how many students would have thought that this would actually be a control law that is workable? Or you can come up with a similar one for here, where you say if the ball is above, then I tilt to the front, and if the ball is behind, then I tilt to the back. That would be the same control law, basically. So here you could say if dp greater than 0, gamma is plus 10 degrees, else. Now here we're just switching between two extremes, so this is called a bang-bang controller, because we cannot actually control the fine degrees, like we don't have analog control over the steering angle or the tilt angle of our plane here. So we implement the very simplest kind of control, just switching between the two extremes. But of course, the idea is if you do that fast enough, then you can have the ball hover in the middle. So unfortunately, that will not work. And I want to use a slightly different example from control theory, or deriving the physical equations. Actually, that's not. So where's my Discord? Yeah, let's just wait for the thing to boot up. Okay, so first thing that I want to do is introduce a slightly easier problem with respect to the dynamics, because the rolling ball on a plane as well as the car, to develop a dynamical model, an accurate dynamic model of that, requires a bit more background in physics. So we will do a very simple one, which is the hovering ball problem. So you have a tube with a ball inside, and you have, so if you have that, then what will happen if you put the ball in the tube? Nothing much, it's going to fall to the bottom, right? Sort of what you would expect to happen. So that's not particularly interesting. So you use your Arduino kit and you add 2 light gates to it. Up and down. Connect them up to your Arduino or whatever other CPU you want to use to control this. If you want to use a digital control system, using 2 digital inputs. And then we make the ball out of metal, and at the top we have an electromagnet that, let's draw it as an actuator. That you can control with your Arduino, and that one you also only have a digital control. You can turn it on or off, the electromagnet. Okay? And then the goal for this is for the ball to hover between the up and down gates. Right? So you want the ball to float in mid-air. And if you implement that very cleverly and train, you can actually make a magic trick out of this by having an electromagnet in your hand and then be the magician that can hover the ball around. But here we just use a tube because we're only interested in the control of this particular problem. So for this, to model it, what information do we need to know in order to simulate this system, in order to be able to then derive a controller for this particular system. So first, try and draw this using Matplotlib. You don't need the electromagnet, but you can plot in the up and down gates, the ball, and then we'll see what information we actually need. I guess it will be the part of it will be the information that you need in order to be able to draw it in the first place. So we want to draw a the hover ball. So I need to have an object for the axis so we can actually plot it. So the pipe is 1 meter wide and 3 meters tall, let's say. And then we draw our little environment. The distance from 0 to pipe height. Draw it in black. And draw the other side. Now, I also later on we may want to animate it, so it's not a bad idea to keep track of the artists that we use to draw this actually. Okay, we have the line objects. And I think I want this. that is. I think I need to. That's how. All right. Okay. That's what's returned there. Okay. Those are the two lines. Now we're going to plot the upper and lower gate. And this one here, maybe I'm going to go minus pipe height divided by 2, pipe height divided by 2. So that 0, 0 will be right in the center of this. Then we make the ball 1 unit wide, so the upper gate should be at let's set a gate margin and a ball radius. And then let's make all that parameterized on the ball radius and some margins. So the pipe width will be equal to the ball radius plus 2 times margin x, and the pipe height would be 3 times the ball radius set the aspect ratio to be equal. Okay. So the upper gate will be at position negative pipe width to pipe width, and the position of the upper gate is equal to the ball radius plus margin y. And then our lower gate will be at this location. By 2 plus So here we have our gates. So now the only other thing that I need would be the position of the ball. And circle requires what arguments? XY radius and then a bunch of other stuff. So X would be D, Y, no, X would be 0 distance would be D. Ball radius. Edge color is black. Face color is red. Edge color. So then we need to draw it. Oh. Yeah. Ball radius, of course. Divided by 2.
Could you need to sign these for job local?
Okay, after the class. Okay.
Oh, sorry, what time?
At 12, when we're finished.
Oh, yeah.
Yeah. So here's our setup. Upper gate, lower gate. I just didn't bother to draw the electronics and the electromagnet. Then we have a ball. Right now the ball is at position 0. And what control do you think you want to apply at this point in time? So the controls that we have would be simply turn the magnet on or turn the magnet off, right? So initially, try and see if we can reconnect. So initially, we start the whole system. Our electromagnet is going to be turned off, right? And then what will happen? Not surprisingly, the ball is going to fall down, right? And that's because the force acting on the ball is going to be F is m times a. Now here we have gravity acting on the whole system. So that means that our acceleration here is going to be g, which is 9.81 meters per second squared. Right? So the ball is going to accelerate downwards. Right? And then it's going to start falling. So the first thing that actually changes as far as our environment is concerned, because we need to sort of check what the system can actually sense or what the state of the system is. The first interesting thing that's going to happen is when that ball has fallen by the distance here, which is our margin, then it's going to trigger our down gate. At that point, then what you want to do is to turn on the magnet. You would think so. Clearly, if the thing is falling too far down and the only sensors that you have are these two gates, then I would think that you definitely want to turn the gate on, the electromagnet on at this point. So, at time t equals 0, we're here, and we start falling down. At what time are we going to trigger the lower gate? Well, in order to figure that out, we need to analyze the motion under constant acceleration. So if I have an object that is at rest at the beginning, then it starts to fall downwards by some distance s, then I want to figure out at which time this is happening. If we're at time t equals 0, we are at position 0, and we cover distance s, and what else do I need? Velocity is 0. So that would be s dot is equal to 0. Then we can derive the equations either by looking up your high school textbook or integrating the equation for velocity. And if you're accelerating with constant acceleration, then what velocity will you have at time t? So if I start at 0 and I accelerate with 9.81 meters per second square, then after 1 second I will be falling at 9.81 meters per second, right? And after half a second I will be falling at 4.905 meters per second. Right? So our velocity is 8 times t. So our distance that we fall is the integral of the velocity. So that will be 1/2 a t squared. So that's that equation. If you can remember this, you can do some cool things. You can throw a rock off a bridge, wait until you hear it plop into the water. You can calculate what the height of the bridge is. Now I want to know, now I have s as a function of t, and actually, since we're dealing with gravity, make that g. Now I want to solve for t as a function of s, so that would be T would be the square root of 2s over g. Multiply by 2, and I get 2s. Divide by g, I get 2s over g. And then that's t squared, so that's the square root of this. So I can now calculate at which time my ball is going to hit the lower gate. Then I can turn on my electromagnet. So at that point, I then need to come up with what's going to happen at that point. So let's say that when we implement it, we use a different number, but to just conceptualize it, let's say that our electromagnet is exactly opposite acceleration of gravity. So if the electromagnet is turned on, then the ball is going to accelerate with minus g upwards. So that means it needs to generate an acceleration of 2g because gravity is accelerating downwards. I want it to go with exactly 1g upwards at that point. That means it needs to generate 2g, which actually would be extremely difficult using an electromagnet because the force that the electromagnet generates would be deteriorating or would be declining with the square of the distance. But we'll ignore this for now. We just have an actuator that will accelerate it exactly upwards with g. So now your ball falls, you trigger the lower rail, you turn the electromagnet on, so then your ball is going to decelerate, right? And reverse direction, eventually it's going to accelerate upwards. And when it hits the upper gate then your control function would be to turn the electromagnet off. So that seems like a simple enough system to build. And there are a couple of practical issues. However, they wouldn't have such a huge impact like air resistance and the fact that the electromagnet, the force that is generated by the electromagnet will deteriorate over the distance, will decrease, not deteriorate, will decrease by the distance squared. If the ball doesn't move much, then we can ignore that particular problem. So what will actually happen to the ball if you implement this system? Well, let's see what happens. So at time t, 0 we're at rest, right? And at rest we have some margins m here. So I don't really care about the size of the ball. I only care about how much gap I have between the top of the ball to the upper gate and the bottom of the ball to the lower gate. So we'll do that, call that M for margin, but maybe that's not a good name because otherwise M is usually mass, so dm, the margin size. So time t equals 0, we start falling. At time t is equal to square root of 2 dm divided by g. Will we hit the lower gate? We turn on the electromagnet. So then what will happen? Now we generate a force, we generate an acceleration on the system. But since we're already falling, our velocity is not 0, right? So I need to calculate what distance the ball is going to fall down here before it reverses direction. So now, even though we hit the gate, we turn on the magnet. Since we already have a velocity falling downward, the ball is going to decelerate, it's going to slow down, but it's going to continue to travel downwards. Now, if the gravity and the force of the magnet are exactly opposite, then how far will this ball fall down before it reverses direction? Well, it's going to fall down exactly the same distance here, dm, because the acceleration is exactly the same. So I can calculate what velocity we have at time t. That would be g multiplied by that. So that would be 2 dmg. But now we're decelerating, so it's in the opposite direction. We're going to fall, if we start 2 centimeters above, then we're going to fall until we're 2 centimeters below. And it's going to take the same time. So at 2t, we're starting to move upwards. That happens at distance dm. So now the ball is accelerating upwards. How far do we need to travel to trigger the upper gate? If we're 0, we need to travel upwards by dm, right? Then we trigger the upper gate. But now we fell 1 dm, right? So we need to go 2 dm upwards to trigger the upper gate. But we also drop down a little bit more before the electromagnet stopped our descent and started reversing direction. So we now have to move up by 3 times dm. Right? So that now means that our equation here, where we can relate the distance to the time, for the first one we would have dm but now we have 3 times that distance. So the time that we need to get to the upper gate would be the square root of 6 dm over g. So at that point, our ball now has accelerated for 3 times longer than before. Before we fell, or we accelerated for distance of dm. Now we accelerate for distance of 3 dm, which means that when we hit the top gate here, our velocity is going to be if this is our time, so our velocity is going to go up with the square root of the distance. This part here. So then we get to t triple dash. We now hit the upper gate, and the velocity that we have will be the square root of 6 dm over g multiplied by g to give us the velocity. So that will be g squared inside of the square root. So the square root of 6 dm g. So then what happens? Then we turn the electromagnet off. However, we already have a velocity going upwards, 6 dm, the square root of 6 dm g. So that means we're going to continue traveling upwards further. Then we're going to come to a rest, then we start falling again. So where's this point here then? Well, here we would have traveled 3 dm, so we'll move upwards by a distance of 3 dm here. And then we start falling downwards again. As we fall downwards, how long until we hit the lower gate? Well, then we have to fall those 3 dm's, right? Plus this one, plus this one. So we'll be falling down by 5 dm, which means that our velocity is going to grow up with the square root of 10 dm now. And the problem is, with this particular control, we end up with unbounded oscillation here. Right? The ball, every time we hit the gate, we're going to keep going faster and faster, which means we drop further and further. Then we shoot up even higher. So it doesn't matter how big your tube is, you're going to start initially and it looks okay, and then eventually you have a rail gun. Your ball will shoot out at very high velocity. You'll have a gun rather than a hovering ball. Right? And so that's the issue with control systems. Even simple things like this, you need to be careful about the physics of it, and you need to think carefully about your control algorithm. So how would you fix that? The problem is here you would need to take the physics into consideration. You have to realize that you're dealing with motion under constant acceleration, and the way to implement that, the way to be able to do that is, what's the crucial piece of information you actually need here in order to come up with a reasonable control, in order to avoid unbounded oscillation, in order to avoid increasing the velocity of the ball as it's shooting through the tube. In order to avoid overshooting here, we would need to know the velocity, right? Now, unless I have a vision system, I won't be able to estimate the velocity just like that. But what we can do is we could use the time at which we trigger the lower gate and the time at which the lower gate is cleared again. Right? And by using that time, we can estimate what the velocity was, which then allows us to modify our control to make sure that we turn it off when we reach, before we reach our zero location here, or before we reach the upper gate location. But that piece of information is crucial in order to be able to do the control properly. Otherwise, your ball is going to oscillate, start slowly, and then it's just going to go wilder and wilder. Eventually, you have unbounded oscillation, destroying your apparatus or shooting out of the apparatus. And it was funny, when I introduced that once to a class in Canada, this particular problem. And there was actually a student that tried to do this for his science project, except they didn't use electromagnet, but they had a styrofoam ball and a fan in the bottom of the tube. And they wanted the fan to blow to keep the styrofoam ball hovering, and nobody told him about control theory, so he couldn't figure out how come his ball kept shooting outside of the tube. Because he thought that was the correct control to use, and without analyzing the dynamics of this, it does have a certain appeal. It's certainly easy to implement, but in reality, this control is not going to make it work. Similarly to this car driving control here, I had a tough time convincing the students that you cannot just implement, if you're to the right of the line, turn left, if you're to the left of the line, turn right, because what will happen to the car is that you will also end up with unbounded oscillation. So if you're trying to follow a path with a toy car with that control, then it's going to oscillate around the path, and it's going to get worse and worse until your car sort of drives like that and then ends up too far away until it just does a circle, because you always you're always turning left at that point. Or yeah, you basically end up driving a straight line by driving this kind of path, which is extremely inefficient for a car. Until you're too far away from the path, in which case you're just turning left and go around in a circle. And the same thing will happen with your ball. If you're trying to roll it in a maze, then it's very similar to the hovering ball problem here, and it's simply going to oscillate further and further away, faster and faster. So now let's have a look and implement that. But we'll do it a little bit more with a couple of more parameters. So I think this is all the information I need in order to be able to draw the system. Let's make this a little bit smaller. So now I want to implement a function. I could represent this as if you are familiar with differential equations, then that would be the standard way of representing this problem as an ordinary differential equation. But without that, what we need to do is we need to take the state of the system into consideration and then integrate it in order to simulate it. So I need to know a point in time. I need to know the state of the system. Now in control theory, that's usually specified as Q. I also need to know the velocity. And then the acceleration. So that will be Q dot dot. Now the acceleration actually is what we can control. So that's usually abbreviated as U. And instead of writing it as a matrix equation, I'm just going to write it as a piece of code. So the new Q's Qx Q dot is equal to Q, state of the system. Then we add our velocity. That would be dt plus qd times dt. And then we return the new state. which would be QX, QD. Now this is numerically not a very stable implementation of the solver for the ordinary differential equation, but for a simple system like this, that is good enough. Then we can define a control function that uses the current position, the current state, and then returns u. And yeah, so if and the margin that I have is margin y, 0.3. And now I just have to get the now I just have to get the directions correct. So if Qx is negative, then U needs to be positive. So let's just integrate our function first. And I guess we can plot it too. So initially we are at rest. And then we also want to plot magnitude. Let's say we want to simulate for 2 seconds with 50 entries. Then we need to calculate what the control is. Next Q would be integrate Q and the control. Oh. I think that'll work. Okay, that is wrong. Ah. And here's our little physics simulation. This is using Euler integration, which is not a numerically very stable system to do. In more complex dynamics, you need to use a proper ODE solver, but for the simple hover ball, this is close enough. So you can see that the ball starts falling until we're at position 9.81, and then we turn on the control here. First we accelerate negative 9.81. Once we go below 0.3, we switch our control, And there I think I should print Q then, not QN. Because that will be the control, yes. So here you can see the velocity and position. So once we hit negative below 0.34, we turn on the magnet, but now we're already falling at 2.40 meters per second. That's our current velocity. Now the magnet is turned on, so we're going to slow down, -2, -1, -120, -0.8, -0.4, and -1.1 velocity. Something is wrong with my... Yes. If QX... Yeah, the control is wrong. If we trigger the lower light bulb, I still want it to continue to accelerate. So Q control, I need to add some more information here. In particular, I need to know what my previous control was. So if it's below this, then it's definitely turned on, else if greater than dm, then it's definitely turned off, else we don't switch the control. Negative 9.81 U because basically this we implement a hysteresis function there. So as we are between the two gates, we don't switch the control. If it's on, it stays on. If it's off, it stays off. I think that should be it. So we're falling until we hit negative 0.3. Then we turn on. Then we decelerate. Then we end up with velocity almost zero. Now here we start moving upwards. Upwards, upwards. Almost zero. Then start moving upwards. Once we are higher than 0.3, we switch our control from electromagnet on to electromagnet off, which means we start decelerating again. So our velocity now is 4. Then we decelerate, start falling downwards until we're below 0.3 again. And the first time we hit the gate, we had a velocity of negative 2 meters per second. The next time we hit the gate, we are at negative 5.2 meters per second. And as if you plot that, you'll see it just keep increasing further and further. So let's plot our function. That is dt, so that should be okay. Make that blue. Cues, anything else that I need to draw? Draw a few. Draw, overball, and that will be Q. And let's draw a little animation. Do we have x-axis? Sim time. Integrate. One, two. So let's see, here's our loop for x in xs. So let's take our artists and add them. QSs, okay. Q0, and what else do we need for drawing the hover ball? AX.
Yeah, let's try it. Back to 3. Okay. And 50 and 51. XS, QS, QS is... Oh, okay. XSI, and then here from this to I. Or plot it like that. QS is okay. So that would be
0.04 I in range x length of x's minus length of q's and then nms on mnm. Then let's see. How come it goes up to 125? Ooh. That is not right. How come? Q is minus 52. How do I end up there? Q is okay, so that's better now. So let's take the simulate it just for half a second. 10. Now let's see what we animate. How does this end up at 30? Q00, Q is 39 point. How do we end up there? Hmm. -1. Okay, so that looks correct now at -0.3, but my gates are in the wrong place. 1.3. Because when I draw them, the gates are in the wrong position, yes. Ball radius divided by 2. So this should really be ball diameter, but I'll fix that later. U previous is -9.81. And now we have our animation here. Five seconds. Negative. Turn it on, turn it off. Okay, how come this is not the correct animation then? So yeah, there you see our oscillating ball now. You can see the position, the blue line, as it keeps increasing, and our velocity as we hit the crossover point. Right? So now I could increase that to get a finer animation, just to show it in more detail. I'll run a little bit longer. And I guess I can draw the upper and the control. Access, use. Zero, and this would be length of use. 151. So now we also show the acceleration that's acting, like turning on, turning off the magnet. And I think that's a pretty nice animation that shows the problem that we have to deal with anytime we're trying to control a system. And like I said, for the hover ball, you need to know the current velocity that you have, and you need to then, therefore you need to time when you hit the lower gate and when you pass the lower gate upwards, because that allows you to then back calculate what the velocity was when you hit it, which allows you to turn off the magnet before you reach the upper gate, right? Because what you want is you want the ball to basically just hover up there and then hit that position at basically zero velocity, right? Then it'll start decelerating again. And so then this is what we have here. Now there's some details of the implementations that I skipped over, but it's good enough to understand what you need to do for the second assignment. Next class we'll be looking at slightly smarter control, because right here with the bang bang control, there's only so much you can do as far as the control is concerned. It's going to be problematic anyway. With the humanoid robot, we have more power in our control because we can change the steering angle not just to plus 10 degrees and minus 10 degrees, or minus 5 degrees and 12 degrees or something. We don't just have digital control, but I can actually set it 1 degree, 2 degrees, 1.5 degrees, right? So we will look next class into how to develop a simple controller that allows us to actually balance the ball on a plane. This one here, the hover ball, I think is a very nice example to show the pitfalls of control theory, which is why to solve this optimally then turns into quite a difficult problem, and that's why all the control theory people are basically handicapped mathematicians. There's a lot of mathematical theory involved in control theory if you've read some of the papers. However, the important part is that the main concepts are actually quite intuitive, and looking at simple examples like that gives you an idea of what the problems are in control theory. No, I didn't want to delete this one. I wanted to delete this one. Okay, good. Now, I also want to announce today that tonight at 11 o'clock, we have the global virtual classroom. Now, this is actually part of the computer vision class, so if you are not in the computer vision course, then strictly speaking, that doesn't apply to you, but it may still be of interest. The Global Virtual Classroom is an initiative by NTNU where the goal is twofold. One, some of the lectures will be given by professors from NTNU. Some of them will be given by overseas university or foreign university. Also, at the end of the lectures, there will be a joint project with students from our overseas partner university. In this case, this year we're doing it together with Ostfalia University, Professor Gernt and his robotics lab in Wolfenbüttel. So tonight at 11 p.m. we will have the first class. If you're interested in that, maybe if you consider an exchange semester abroad, or like what you're doing. I mean, for you it would be the reverse, right?
I'm considering to go back to Germany.
Yes, yes. Then I think that would be a very good opportunity to just see how stuff is run and done at other universities, not just NTNU. So it'll be in the Robot Vision channel. Taiwan time. What date is today? Be Monday, 20th November. So the project that we're working on for the computer vision class is actually pretty neat. Bamboleo. No. How come? The goal is to implement this game on a robot. So the robot arm has to play this Bamboleo game.
For years, Bamboleo, because this game essentially comes with this giant wooden plate that you're going to be balancing wooden pieces upon.
And you have different pieces.
Sounds like a lot of fun. I've liked some of the other games like Hamster Roll. Let's see how good this one is. So first you start with this big yellow wooden board, pretty sturdy,
It's actually
and on
sort
top
of
of this
similar
board
to
you're
the
going to be
2D
putting
version
all sorts of objects. Now you'll see on here you have some rectangular prisms,
you need an arm
you have some pyramids and cones
take
and
off the different
cylinders.
pieces.
This
The
one has a
different
hole in
pieces
the
have
middle.
different weights.
And so you're going to want to put these around it on the outside edges, or spread them out as evenly as you can. Then you have this piece here. This is basically a cork ball on top of this wooden stick, and then we're going to take this and we're going to balance it on top of this. So you're just going to move it around till you feel like it's going to stay there. Whoops. And it's really hard because if stuff slides, then it becomes that much more difficult. So a little bit that way, a little bit that way. There we go.
So now it's balanced.
So now it's sitting there
and
balanced
then
on a thing. On a
as
player's
a player,
turn,
you have to pull
they're going to
pieces
just
off.
simply take a piece
If you pull one
from
off
here,
and it tilts, then
and they're
you
going
lost,
to
right? So you
take
need
it
to
off.
For the robot, needs to calculate
You
the
take the
center
piece
of
off
mass.
and you keep it. Then it's the next player's turn. And they're going to take a piece off and keep it. So I would take this one off.
Then you have another one.
Now, usually you're going to want to take a piece off the side that's tilting downward. So maybe the next person takes this piece off. And as you take these pieces off, you're trying to keep the whole thing from collapsing. Eventually,
And then it
the whole
tilts,
thing
so
is
then
gonna
you
fall
would have
down.
lost the...
now, when it falls down, you lose 4 pieces.
I think
If
that's
you don't have
actually
4
a pretty
pieces,
nice game
you go into
to try and
negative points.
implement on
And you're
the
going to keep
humanoid
track of your
robot.
points that way.
Requires good
So
vision because you need to know
eventually
the
you're gonna-
position of the things.
I really have a hard time figuring out how anyone's going to get positive points because it falls
You
over.
need to recognize what type of object it is in order to know what the weight is. And then once you know the weight and the position of the different pieces, you can figure out which piece you want to pick up. And then our partners in Ostfalia will be the ones responsible implementing the control using a Sawyer robot to pick up the various pieces. So if you're interested in that or just to learn more about foreign universities, you should join the Discord channel tonight at 11 p.m. The time is so late because of the time difference with Germany. They're 6 hours or 7 hours behind us. Okay, good. Then that's it for today, and I will see you all next Monday.